All right, now I think it's running. So let's see. I hope that shows up. Okay, I don't know. We'll see. So they come out looking homemade. So, there you go. And so, without further ado, I'll give this time to start. Like that. Running. I'll start over here. I'll make note the weather was not good today, so if you're here, it's a star in your plan. So let's put it that way. Okay. Now, last time, as I recall, we were talking about ions. Okay. And what is the difference between an atom of something and an ion? Let's take sodium, for example. What's the difference between a sodium atom and a sodium ion? Ion has a charge. Atoms have a charge of what? Neutral. 0. All right. Why is an atom neutral? What makes it neutral with respect to charge? Same number of protons and electrons. Right. Okay, and in the case of sodium, I think it's got something like 11 protons and 11 electrons. How many valence electrons does sodium atom have? 1. All right, and it's a metal, so it tends to give up that 1 electron when it forms bonds, and so therefore we end up with a charge now of +1, because we still have 11 protons, we now only have 10 electrons. If it's given it up, it becomes a cation with a +1 charge. All right, so there we go. Now, the other kind of ion that we can have are what are called anions, right? And what kind of charge do those exhibit? Negative charges. Why negative? How are they formed? All right, right. A neutral atom, in the case of an anion, acquires extra electrons and sticks them in its valence shell. Why does it put them in there? Why does it even want them? What does it do with them? Fill up the valence shell, right. Just like the cations got rid of a few electrons that they had in their valence shell, so now the next lower shell automatically becomes really the valence shell. It's filled. The anions are going to be atoms that have nearly filled valence shells. They're going to take in extra electrons, fill it up, and get a filled valence shell that way. And as we noted, metals tend to form cations and non-metals tend to form anions, right? And we know when we look at the periodic table how to tell metals from non-metals. We chatted about that last time. All right, so let's just go back over some of these and we'll add to it. All right, what is the name of this ion? Hydrogen. All right, if it's H plus 1, it's hydrogen. That's one name for it. What's the other name for it? Proton, right? Proton could be either a hydrogen ion or a proton. Remember, I think we talked about how we can get away with that name, right? Okay. All right. Now, the H3O is a +1 charge. What's that one called? What's the name of that one? Hydronium ion. Right. Now, the hydrogen ion, the H plus 1, that's a monoatomic cation, right? And the H3O plus 1 is a polyatomic cation. What's the difference between monoatomic and polyatomic? Mono is derived from a single atom. Polyatomic is more than one atom that has acquired the charge. They're bonded together and they've acquired the charge. Okay, what about this one? What's this one called? Sodium ion, right? And this one is potassium ion, and that one is magnesium ion, and that one's calcium ion, yes. Now, what about these? All right? That was magnesium, that's calcium, but what's the name of this one, the Fe with the +2 charge? Iron 2, or if we go with the suffix name, it's ferrous. All right. Now, whenever there's more than one charge, you've got to specify which one it is. And that's true with the irons. So the iron with the +3 charge is called either with the stock name, iron 3, or the suffix name, ferric. And when it comes to the coppers, the +1 is called either with the stock name, copper 1, or the suffix name, cuprous, right? And the +2, copper 2, or cupric. All right, and then we have this one, which is barium. All right, you notice that one only has one possible charge. It's always +2. Zinc is always +2. But manganese isn't. But the most common one is this one, and that is manganese 2. All right, so we're not going to worry about the suffix name there. Well, let's go to the anions. We haven't got to them yet. We don't want to slide them. They're most important. Oh, ammonia. Shame on me. I forgot about that one. That's a polyatomic cation, right? Okay. Now, chloride. That's a monoatomic anion. Monoatomic. Why is it monoatomic? Derived from a single atom. All right, now I want to say a word or two about the naming conventions here. All right, we don't call it chlorine ion. It's called a chloride ion. Kaboom. All right. Now, if it is a monoatomic anion, like that, the name in this case is the chloride ion. It has that IBE suffix. So whenever you see the IBE suffix on the end of the name, it designates the monoatomic anion. Monoatomic. Okay? If we're going to see some polyatomic versions of things here in just a bit. And there's going to be some slightly different suffixes for those. All right, so continuing on. The next one I believe is fluoride. Yes, all right, so that would be fluoride. All right, and chloride and fluoride are always -1 because, I mean, let's look at the table. How many valence electrons does a chlorine atom have? How many does it have? 7. And how many does it want? 8. It's only got room for really one more. So if it acquires one more, then the chlorine has now picked up an extra electron, become a chloride ion, and it has an electron configuration like argon, which is the noble gas right beside it there on the table. Filled valence shells. All right, next one on the list is one of our polyatomic anions. And it has a friend, and I'm going to put that one up there too at the same time because I want to talk about them together. So, without further ado, oh, how nice. They're up there on the board. I can write beside it. This one is called the nitrite ion, I-T-E on the end. And the next one is called the nitrate ion, A-T-E on the end. Now, what do you notice about it? They're a combination of nitrogen with oxygen, right? Which suffix goes with the one that has fewer oxygens? I-T-E. Which one goes with the one having more oxygens? A-T-E. Right. Nitrite, nitrate. NO2 minus 1, NO3 minus 1. Now, let me ask you this. This one isn't on the list, but we ought to be able to figure out the name. Suppose we have this. What would be its name? Well, it's a monoatomic ion, right? Monoatomic anion. So what suffix is it likely to have on it? IBE. Well, I'll bet you couldn't guess in a million years what the name would be. be correct if you said nitride. Now see how easy that is? Isn't it? Yes! You know, just remember a few little rules, you can't go wrong. Now the number of oxygens, well, it's always going to be 2 and 3. You got to just know that. But if there's one with fewer oxygens, it has the ITE suffix. The one with more oxygens has the ATE. And then if you go above and beyond that, or below that, there's another thing. But I don't think we're not going to worry about that today. All right. Well, let's just continue on. Let's see. Hunting down my remotes. All right. Now, what would be the name of this one, I wonder? Sulfide. Right. Why? Why is it IDE on the end? Monoatomic ion. Right, monoatomic anion. All right, next one, I think, is combo. Indeed it is. And this is sulfate, SO4 with a -2 charge. All right, now I didn't give you sulfite, but it's SO3 with a -2 charge. All right, so if you had that one, that's what it would be. We didn't worry with that one. Okay. Well, let's continue on. Put the screen down. Can't really. All right, so continuing on. Next one we have is called phosphate. Phosphate, ATE. All right, PO4 with a -3 charge. All right, if you had just phosphorus, just P -3, what would it be called? Phosphide, yes. All right, oh, I love this one. CO3, -2 charge, carbonate. In fact, I'm going to put the screen up on this one and the next one. Together nicely. Some of this. All right, this is carbonate ion, all right. And then the next one is a combination with some hydrogen in it. And this one actually has 2 names. Now, the one we're typically going to use is bicarbonate. But it has another name. It can also be called hydrogen carbonate. All right, and remember now, that's 2 words. It's not something contracted together. Bicarbonate, hydrogen carbonate, one and the same. HCO3, -1 charge. All right? And basically it's formed by taking a carbonate and sticking a hydrogen on with it. All right, now that's pretty simple, isn't it? Now, a couple of others. All right, any thought about what this one would be called? It's just oxygen with a -2 charge on it. Oxide, yes. All right. And then, I think we have one more, which I don't think these are on the list in the outline, but you can write them in, and you can do a few things for yourself, right? All right, I don't want to get it to show up while I'm pointing at the thing, I guess. There it is. Oh, yeah, this is a classic. This is what's called the acetate ion. C2H3O2, charge of -1. C2H3O2, charge of -1. Acetate. Oh, you know, look at that. I mean, that's impressive. Write that one on a napkin at dinner tonight. Impress everybody. All right, what you learn. All right, very nice. Okay, there we go. Now that's simple, isn't it? Yes, but here's the deal. You've got to make them your own. And you got to recognize them when you see them coming down the street as broad as life and twice as natural, what they are. And don't get creative with names. because you get creative with names, I call out the old red ink. So, it's time now to put them to use. And so, we really don't need the projector right now, so we'll just squelch that, and I'm not looking for that being dazzled by it. And see, this is alright, now, let's use some of these cations and anions, and first let's start writing some formula, unit formulae for ionic compounds. Now, what, first of all, do we mean by a compound? Well, let's go back. What is an element? We've defined that before. How would you define an element? What was an element? Well, let me start it for you. That'd make a nice question on these days, wouldn't it? Give it the definition of an element. It's a pure substance, right? Which cannot be broken down into anything simpler by chemical means. Right? That sound familiar? Yes, we've said it before. Alright, pure substance, which cannot be broken down into anything simpler by chemical means. That's an element. What are elements made of? Collections of what? Atoms. Right, chemically identical atoms. Well, compounds are a little different. They are going to contain more than one element. So these are going to turn out to be pure substances, a pure substance which can be broken down into something simpler by ordinary chemical means. Now, as we're going to find out, not today, but soon, we're talking about chemical means, we're talking about chemical reactions. So if you carry out a reaction, you can break a compound down into some simpler things. And you may get smaller compounds, or you'll more often than not get elements, get atoms, all right, when you break it down. So in essence, elements get formed into compounds when you combine two or more different elements together typically. All right, now, if they're ionic compounds, then that indicates the presence of ionic bonds. And I know we've defined that one before. What is an ionic bond? What was the definition of an ionic bond? Huh? Yes, force of attraction between oppositely charged ions. Alright, force of attraction between cations and anions. Okay? There you go. That's what it is. So we're dealing with ions. We're putting ions together to form these things. And, as you will see, these ionic bonds are pretty strong because most ionic compounds are solids at room temperature. Alright, well, let's go through a little procedure for doing this. So let's start, got to start with the name. So let's take something like flesh. Potassium fluoride, that would be the name of an ionic compound. That's made of two different ions. There's a cation, there's an anion. By convention, the cation is usually the first name. Alright? That's what's named first. Second name, anion. Alright? And you'd know that, really, anyway. But, you know, but there it is. Alright, so there's a name. We want to write the formula for it. And the formula for it is called a formula unit formula, remember. And a formula unit is the smallest sample you can have for the ionic compound. All right? Formula units are the smallest sample you can have for an ionic compound. And formula units are electrically neutral. Now, there's something you want to remember. Formula units are electrically neutral. So guess what? When you go adding together the cation, anion charges, what are you going to get for your efforts if you've done it properly? 0. All right. Now, here is a little process. So we're going to do this in steps. So the first thing we want, the formulas for the ions. So, what is the formula for the potassium ion? Give me the symbol and the charge. Yep, thank you. K plus 1. And for the fluoride ion, what is the formula for that? Symbol and charge is F minus 1. Excellent. All right, there it is. Always start with that. Now, this is not final form. We're going to do it in steps. All right, so the first step is getting these ions written down. Now, the next thing we want to do, sum the charges. All right, potassium is plus 1, fluoride is minus 1. What do you get when you add together a plus 1 and a minus 1? 0. All right. Now, if the sum is 0, then all you need is one cation bonded with one anion, and it's done. So now we're just going to put it in final form, which is going to be Kf, and there it is. There it is. All right? Pretty simple, is it not? 1 potassium, 1 fluoride. And that gives you a formula unit of potassium fluoride. All right? Simple. And we can check, because we already know potassium's plus 1 and fluoride's minus 1. You add those two numbers together, you get 0, and there it is. All right? It's a 1-to-1 cation-anion ratio in that case. All right, well that's simple, isn't it? Yes. All right, now, let's kick it up a notch. I'm going to keep fluoride, but I'm going to get rid of potassium. This time I'm going to go with calcium. I want calcium fluoride. Well, once again, write the ions. All right, what is the formula for the calcium ion? Ca plus 2. All right, and we've got the fluoride there, F minus 1. All right, now, sum the charges. So we've got a plus 2 and a minus 1, and what do we get? We end up with a plus 1. Well, I think we would agree that is not 0. Okay? So if it's not 0, well then we're going to have to do something else. That's easy. All right, what are we going to do next? Well, we're going to go with what we'll call trial subscripts. All right, trial subscripts. So I'm just going to bring these over here. There's my calcium, there's my fluoride. And here's what I'm going to do. I'm going to take the absolute value of the cation charge. Now, the cation charge is plus 2. What's the absolute value of plus 2? 2. And I'm going to make that absolute value of that cation charge the trial subscript for the anion. Just bring it right down there. All right? Now, I'm going to take the absolute value of the anion charge, and I'm going to bring it down as the trial subscript for the cation. All right? The anion in this case is -1. What's the absolute value of a -1? 1. All right, now, even though we're writing as a trial, we don't actually use 1 subscripts in anything. All right, so let's put it now in something that more resembles final form, and then we'll check it out. So if we go with that, we're going to have 1 calcium and 2 fluorides, right? And there it is. 1 calcium, the 1 understood, but anything above 1 we got to write, so 2 fluorides, there it is, CaF sub 2. All right, now let's check it out and see if this is electrically neutral. There's 1 calcium, and they're each +2, right? And there are 2 fluorides, and they're each -1. So what do you get when you add together a +2 and a -2? You get 0. So it checks out. Now, there it is, and there's just one more thing to check, and most of the time you won't really have to worry with this. But here's the deal. In a formula unit formula, you want the lowest integer ratio between the cations and anions that yields an electrically neutral formula unit. Now, what's an integer? That was a mouthful of stuff. What's an integer? A whole number. All right? So what is my cation-anion ratio in this calcium fluoride? As I've got it written up here. 1 to 2. That's the ratio, right? That is an integer, is it not? 1 to 2. Can I factor anything out of that and reduce that down and still have an integer ratio? No. So it's done. That's it. That's it. Lowest integer ratio to give an electrically neutral formula unit. That's what you want. There it is. Doesn't get any simpler than that. Right? Cake. All right, now. All right? No problem with that. Well, let's kick it up a notch. Let's do calcium carbonate. All right, we know what calcium is. So what's calcium carbonate? What's the carbonate formula? Yep, CO3 charge of -2. Okay? Now, what's the next step? Sum the charges. +2 plus a -2. What does it give me? 0. All right, and in this case, the sum is 0. So what do I know? What do I need to put it in final form? Right, 1 cation, 1 anion. So all I've got to do is write 1 cation, that's Ca. The anion CO sub 3, there it is, CaCO3. That's it, there's calcium carbonate. All right? Don't need to add any subscripts, right? Didn't need them. Okay? Now that's simple, isn't it? Well now, let's kick it up another notch. Oh, I don't know. I'm getting tired of calcium. Let's go to zinc. And I don't want carbonate this time either. I want zinc bicarbonate. All right, now, zinc. What's the formula for that? Yep, Zn plus 2. And bicarbonate is, yep, HCO3 with a -1. All right, well, let's sum the charges. We've got a +2 and a -1, and that gives me a +1. Not 0, is it? Well, what am I going to have to do? Come up with some trial subscripts, right? All right, now, what am I going to make for the subscript on the zinc? What's going to be the subscript that I need for that? A 1. All right, so we're going to say absolute value of that, bring it down here. There's a 1. Now, what about the bicarbonate? Absolute value of the charge on the zinc, which is 2. Bring it down over here. There's the trial subscript on the bicarbonate. Now, there's another wrinkle to add to the proof this time. All right, there's the zinc. Only need one of them, don't need a subscript. But how am I going to apply the subscript of 2 to that bicarbonate? Well, it's very easy. I'm going to do it like that. Anytime you have to apply a subscript other than a 1 to a polyatomic ion, it doesn't matter whether it's a polyatomic cation or a polyatomic anion, but anytime you have to apply a subscript other than 1 to a polyatomic ion, you write parentheses around the polyatomic ion formula and apply the subscript following the parentheses. All right? Let me say it again. Whenever you have to apply a subscript other than 1 to a polyatomic ion, put parentheses around the formula of the polyatomic ion and apply the subscript following the parentheses. All right? Have to put a subscript other than 1 on a polyatomic ion, put parentheses around the formula of the polyatomic ion, and follow the parentheses with the subscript. There it is. So when anybody looks at this, they can see it's zinc bicarbonate. All right? And there you go. Now how are you going to know it's bicarbonate? Because you've memorized it's HCO3 is the bicarbonate ion formula. All right. That's exactly how you want to recognize it. All right, and there we go. 1 zinc, 2 bicarbonates. Don't go distributing the 2 out here, so I don't want to see like ZnH2C2O6. That doesn't mean a thing. All right? And certainly not like ZnHCO6. I mean, that means nothing either. This is the proper way to do it. Now, if it's a polyatomic ion and the subscript is understood to be 1, leave the parentheses off. Well, we'll do one of those. All right. All right? Well, let's just go with this. Let's suppose we want sodium bicarbonate. All right? Sodium bicarbonate. All right, what is the formula for the sodium ion? Na plus 1, and we've already got the bicarbonate up there. It's HCO3 with a -1 charge. All right, we sum the charges. We've got a +1 and a -1. Well, that gives us 0. So it is 0. So what do we know? We just need 1 of each, right? How's it going to look? NaHCO3. Why did I not put parentheses around the bicarbonate formula that time? Because I only need 1 of them. If you only need 1 of them, leave the parentheses off. Okay? You only need 1 of the polyatomic ions to complete the formula. Leave the parentheses off. Okay? There you go. Well, that's simple, isn't it? All right, well, let's do something else. Let's do another one. All right, this time, let's see, what would be a low one? I like it. Let's go with ferric sulfate. All right? Ferric sulfate. All right, what is the formula for the ferric ion?
Fe plus 3.
That's it, Fe plus 3. And for the sulfate, it's, that's an A. Sulfate is, yep, SO4 with a -2 charge. All right, now if we sum the charges, +3 and a -2, we end up with +1. Oops. And that's not 0. So now we got to do the trial business. All right, so what is going to be the trial subscript now for the iron? A 2. And for the sulfate, it's going to be a 3. Well, now if we put it in final form, what are we going to have? Fe2, and then in parentheses, SO4, 3. Like that. Why did I need to put parentheses around the sulfate formula? Because I have to put a subscript on it, something other than a 1. All right? Now that's simple enough, isn't it? Well, let's check this out. What is the cation-anion ratio this time? Just look at the subscripts. 2 to 3. 2 to 3 is the cation-anion ratio. Is this electrically neutral? Well, let's check it out. I've got 2 irons, and we said these are each +3, right? I've got 3 sulfates, and we said each of them is -2. Well, there's a +6 and a -6. That gives me 0. It is indeed electrically neutral. All right? And it's the lowest possible integer ratio between cations and anions. It gives me a neutral compound, so that's it. There it is. So there's the final form for it. Fe2, SO3, or excuse me, SO4 in parentheses, 3. There it is. Done. Simple. Right? Yes. Oh, let's just do one more for kicks. Let's do ammonium acetate. Now that'll be an impressive one. All right, what is the formula for the ammonium ion? Yes. NH4 charged to +1, acetate, right, C2H3O2 charge of -1. All right, sum the charges. I think it's going to give us 0. So, what is it going to be in final form? What's going to be the final form for the formula, unit formula of ammonium acetate? Now see how easy that was, and look how impressive that is. Ammonium acetate, NH4C2H3O2, there it is, all tied up in a nice neat package. Right? Right. 1 ammonium ion, 1 acetate ion. All right? Now how are you going to know that? Well, you're going to recognize that NH4 is ammonium, and you're going to recognize that C2H3O2 is acetate, and you're not going to give me some creative name, because if you do, the red ink comes out, you won't have to worry about that red ink. You're not going to make those kinds of mistakes. All right? Well then, we've been writing formulas. Now let's turn the train around and down the track the other direction. I'm going to give you a formula. You're going to give me a name. All right? All right, so let's just start with this one. All right, now when it comes to writing names, basically all you're going to do is this. You're going to give the name of the cation, you're going to follow it with the name of the anion. That's it. That's all you do. Don't worry about subscripts. We're not really going to pay any attention to how many of these things are there, because, you know, we automatically can figure that out from the formula. All right? Because we know the charges on these things. So what is the cation in this case? It's magnesium, yes. And what is the anion? I didn't hear that correctly. Bless you. Magnesium sulfide. Right? There it is. All right, there it is. We've got the magnesium ion bonded with the sulfide ion done. All right? Well, that was simple, wasn't it? Well, let's do another one. All right, this time, let's suppose we have something like that. What would that one be? Well, again, name the cation. What's the cation? Sodium. What's the anion? Yes. Done. That's it. That's all you got to do. Well, let's try it. All right, now, cation this time. Well, we know it's iron in some form, but what do we know about iron? It can either be iron 2 or iron 3, and we've got to specify which one it is. But there's an easy way to figure it out. All right, very easy, because here's the thing we know. We know that whatever the charge on that iron is, plus 3 times whatever the charge on the chloride is, and we know it's -1. What's that got to equal? It's got to sum up to 0. Looks like a little simple equation to solve, doesn't it? That's all it is. All right, now, you may not know what the cation charge is off the bat when you've got these where there could be more than one possible charge. But you always know the anion charge. Remember, the anions only had one possible charge. They didn't have more than one. You'll always know it. So it's easy to figure it out. All right, so we know that that chloride is -1 each, and there are 3 of them here. How do we know there are 3 chlorides here? Got that subscript of 3 up there, right? Well, what is the charge on the iron? +3, right? All you got to do is solve that out. So you got iron plus a -3 equals 0. Move that -3 over here. That's going to change the sign to plus, right? The 1 iron plus 3. So now we can name the compound. So now what's the name? Iron 3 chloride, if we use the stock name. And if we use the suffix name, it would be ferric chloride, yes. Now, pretty simple, is it not? Yes, that's all there is to it. That's all there is to it. All right, because remember, if you're dealing with copper or you're dealing with iron, they can have more than one possible charge. You've got to figure out which one it is. Easy to do. Just remember, you know the charge on the anion, and the formula always tells you how many of them are there. And the total positive charges, total negative charges have got to sum up to 0. Right? So it's just a matter of solving what you don't know, and that's whatever the charge is on the cation in this case. All right, well, let's do another one. Let's do another one. All right, what is this one? Well, we've got to figure out which copper it is. Now, what do we know? There are 3 coppers, right? All right, and there are 2 phosphates. What is the charge on phosphate? What's the charge on a phosphate ion? -3. All right? All that's got to sum up to equal 0 because the formula unit is electrically neutral. Okay? Well, what have we got? 3 coppers plus a -6 equals 0. So, what is the charge on the copper? +2. Well, let's have the name. Stock name would be copper 2 phosphate. And the suffix name would be cupric phosphate. And there it is. Now, there's nothing hard about that, is there? Is there? No! There's nothing hard about any of it. Now you just need a little practice. On the web page, there is a little practice sheet. Now let me find it because I never know what the name of it is. Okay, here it is. Chemistry Practice Problems. It's a 2-pager. All right? And back here it is. I'll show you what it looks like. There it is. Chemistry Practice Problems. It's on the web page for Exam 1 materials. Page 1, the name is given. You write the formula, unit formula. All right? Page 2, the formula is given. You write the name. All right? So there's some practice. You got 10 of each. All right? Shouldn't be hard to do. Work on that over the weekend. That will keep you out of mischief for probably all of, I don't know, half an hour if you have any problems. You shouldn't. All right. And we'll take a look at that come Tuesday. Okay? Or Monday, in the case of the Monday people, if they're watching this. All right. Now that's pretty simple, isn't it? Good heavens, yes. So, ionic compounds shouldn't be any real problem. If they're made of ions, they're ionic compounds. Now, for the most part, what gives them away? If it's a metal and a non-metal, it's probably ionic. Because remember what happens when you bring metals and non-metals together. The metals tend to give up their valence electrons, the non-metals tend to take them up. Because non-metals tend to have, remember, higher electronegativities. Okay? Now, there are some, that don't fit that don't conform to that, like, if we put, let's say, ammonium with acetate and make up that ammonium acetate, like I think we may have had up there a bit ago. Well, all those are non-metals, but that is still an ionic compound. Why? Well, it has ionic bonds between the cation and the anion. What's the cation in this case? Yes, and what's the name of NH4? Ammonium. And that's the anion. And what's the name of that anion? Acetate. Now that's simple, isn't it? Yes. Okay. Ionic compounds made of ions, cations and anions. Very simple. When you name them, name the cation, name the anion, done. When you write the formula, cation comes first, anion second. All right? Cake. Well, now, there we go. Ionic compounds, ionic bonds. What's an ionic bond? What was an ionic bond? Force of attraction between oppositely charged ions. That's exactly it. Now, time to kick it up another notch. Ionic bonds, ionic compounds, ions, right, good. Now, the next prune or wrinkle on the prune concerns another type of bond. And that's what we call covalent bonds. Now, how did we get ions? We had atoms that either lost or gained electrons, right, from their valence shell. Covalent bonds are going to be a bit different. In this case, two atoms are going to come together and share pairs of valence electrons. It's not like one gives and the other takes, but they both contribute and they share them out. Well, that sounds nice, doesn't it? Doesn't it? Yes, it is. All right, so what's a covalent bond? Covalent bonds form when two or more neutral atoms come together and share pairs of valence electrons. Why are they doing it? To get a filled valence shell. This was the third strategy, remember, that we said could be used to attain a filled valence shell, which is far more stable. All right? So rather than giving them up or taking them, they just come together and they share them. And by sharing pairs of valence electrons between two atoms, they form a bond. That's called a covalent bond. Now, what is the structural formula of a covalent compound? Well, it's called a molecule. All right, remember, what do we call the structural unit for an ionic compound? A formula unit, right? Remember that was the smallest sample you could have? All right? Smallest sample you can have of a covalent compound is a molecule. All right? And just like formula units, the overall charge on a molecule is 0. It's electrically neutral. Well, it's going to be easy to remember that, because remember, all we're doing here are taking neutral atoms and combining them together, and they form an electrically neutral molecule. You know, there isn't any charge as such showing up here. You start with neutral atoms, you end with a neutral molecule. All right, you don't have to add any charges together this time. Why do you all look so unconvinced of that? Well, we'll find out. All right, another wrinkle for the prune. When you're forming covalent bonds, you're typically forming them between non-metal elements, I should say. All right? In fact, some people may refer to covalent compounds as non-metal compounds. All right? So if you go to the cocktail party, and in one cluster of the room there's some folks talking about covalent compounds, and over in the other corner of the room they're munching away on something and chattering about non-metal compounds. They're probably talking about the same thing. All right? All right, there you go. All right, now that's simple, is it not? Where do you find on your friendly neighborhood periodic table, where do you find the non-metals? Over on the right. Yes. All right. Now, a few other wrinkles for the proof. There are two basic types of covalent bonds. All right? One type is what we call a regular covalent bond. Regular. All right? Most of the time, this is what we're going to encounter. All right? By far. Now, what is it? How will you know it when you see it coming down the street as broad as life and twice as natural? Well, if it's a regular covalent bond, each atom of the two bonded atoms, each atom, contributes one electron each to form the bonding pair of electrons. Bonding pair, shared pair. All right? So each atom of the two bonded atoms is contributing one electron each to form the shared pair of electrons that constitutes the covalent bond. All right, now that's simple, is it not? heavens, yes. So, if I've got atom A and atom B, this one, A, is going to give an electron from its valence shell. And this B is going to give one of its valence electrons, and they're going to share them out. They're going to spend time with A, and they're going to spend time with B. And by spending time with both of those atoms, the two atoms are held together, bonded together. That's a covalent bond. If they're sharing a single pair of valence electrons, we're going to call it a single covalent bond. Single covalent bond, one pair of electrons shared between the two atoms. Now that's simple, isn't it? Wonder what we're going to call it if they share two pairs, because there's some that do. A double covalent bond. So what's a double covalent bond? Two atoms share two pairs of valence electrons. Two pairs. Where do they come from? Well, in each pair, one of the electrons came from the one atom, say atom A, and the other one came from atom B. You know, they equally contribute, and then they share them out. All right? We can kick it up one more notch. There are going to be some cases where we encounter what's called a triple covalent bond. I wonder what that means. Two atoms sharing three pairs of valence electrons. Yes. And if they're regular covalent bonds, where do they come from? Each pair would have one electron in each atom. Each of the two atoms. Okay? Now that's simple, isn't it? So if it's a regular covalent bond, it's a shared pair of valence electrons between two atoms. Where do they come from? One from each. Equal contributions. Now you probably guess what the next case is going to be like. And that's what is called a coordinate covalent bond. All right? What about that? Well, this is akin to you come to my house for the duck dinner, you bring the duck. One atom is going to contribute both of the electrons of the bonding pair. But the other one's going to come along and share with it. Not equal contributions this time. One of the two is giving both electrons to form the bonding pair. And the other atom is going to be there to share. Now, this is not going to be seen terribly often. There are a few compounds that do this, but mostly where you encounter these, most of the time, you're going to encounter these with polyatomic ions. Polyatomic ions very often are going to show coordinate covalent bonds in there somewhere. And how are you going to know? We just have to chase them down. We're not going to do that today because I can tell you're all wilting on the vine. So anyway, but there's just one more slide that I want to show you, and then we'll say that you got your money's worth. And it's this one. All right, now there we have a couple of hydrogen atoms, right? How many valence electrons does a hydrogen atom have? Just one. How many would it like to have, though, in order to have a filled valence shell? It'd like to have two, right? Because the one lonely electron is in the first shell, and two is all it takes to fill it up. So it really wants to be more like helium, its neighbor over there on the other side of the table, that has two electrons in that first shell. Well, what happens? Well, two hydrogen atoms very often come together and share a pair of valence electrons. All right? So here they are. This one's got one, this one's got one. They put them together. We now have a shared pair because where are they going to spend their time? They're going to spend their time in orbit about both nuclei. And when they do that, they form a regular covalent bond, a regular single covalent bond between the two hydrogen nuclei. All right? And that gives us a molecule of hydrogen. Now, hydrogen is one of 7 elements that, when they're uncombined with anything else, form these 2-atom molecules. All right? So, hydrogen gas, it's a gas. I don't think that's a shock to anybody, right? Remember the Hindenburg. All right, hydrogen gas is made up of hydrogen molecules. Okay? 2-atom molecules. There we go. And between the 2 hydrogen atoms in the hydrogen molecule is a single covalent bond, a single regular covalent bond. Why? Because each hydrogen atom gave 1 electron each to form it, and the 2 electrons are now a shared pair between the 2 nuclei. All right? Now that's simple enough, is it not? Well, we will spend more time with this on Tuesday, I can assure you. Because, as I said, there are 7 elements that exist this way. I like to call them my gang of 7. And we're going to find out who the other 6 are. They're really easy. You know, you just have that old periodic table handy. You can just get a multitude of info from it. All right? So you work on your ionic compounds, writing formulas and naming compounds. Bring that with you. And then we're going to talk more about molecules. And I'll bring my little box of goodies back, where we've got some nice models for shapes of molecules. This is the cakeyest, easiest thing. And we'll go a little deeper than that. So, enjoy. Be careful.